Lukowski, so you have until dinner time, basically. I won't interrupt you, and he'll be telling us about canonical differential equations for cosmology.
Thanks a lot. So thanks a lot to organizers for inviting me to weekend, to Lauren and to So what I would like to talk about today is the work which we've done with Rita, who is here in the room, and our two PhD students, Mattia and Sandro Palazzo, who are our students at the University of Hertfordshire. And that work was published a month ago, a little bit more than a month ago. Still waiting for sending to the journal. But, what I want to do, so this meeting is focused on the Amplituhedron, and I am really fond of Amplituhedron, and especially I'm really fond of the multiple Amplituhedron, but I will not be talking about this. However, I want to just emphasize that almost every talk which we heard in this meeting follows similar pattern. So it focuses on problems where three very important pieces are kind of emphasized to various degree, but usually what we discuss some physics problems. So physics gives us motivation for problems, like for example, n equals to 4 super scattering amplitudes. And what we try to do, we try to find some very, very natural and good mathematical framework, and what we end up with very often, at least in this room, we end up with some intersection of geometry and combinatorics. So if you take n equals to 4 super scattering amplitudes, that would be geometry of Amplituhedron, one to Amplituhedron, and combinatorics of, let's say, positive plus minus into boundaries or related things, cluster algebras. If you take phi cube theory, then the geometry will be a sesahedron, and the combinatorics will be a combinatorics of trivalent graphs, for example. So what I want to talk about today, we have similar patterns. So there will be some physical motivation, and I would just just say what this physical motivation is, and then we will focus on one particular quantity which we want to calculate in some particular physical theory, and then we forget about physics, and I will move to combinatorics and geometry and show how it is reflected in this problem and how it helps to solve the problem at hand. So for non-physicists in the room, I will be very brief with my physics introduction. I just wanted to kind of mention what type of physics we are doing here, but most of my talk is really focused on mathematics of this problem. So the physical problem which we are considering here is related to cosmology. To be more precise, it's a power law FRW cosmology, which is a toy model for cosmological theories. It will be a very simple theory, but already there are some quite interesting behaviors and quantities which we can calculate and play with. And the combinatorics, which I'll be using here, is the combinatorics associated with some objects which I will define here, which are called tubes and tubings on graphs, which one can understand if you're a physicist, you can understand them as Feynman graphs. And the geometry here, there is some positive geometry which is underlying all this construction, and it will be much simpler than Amplituhedron. This geometry will be, it will really a polytopic geometry. So everything will be kind of straight surfaces here without any higher order polynomial behaviors. Okay, sorry, right direction. So let me start with the physics motivation. So the next 3 slides, if you're not a physicist and you're not interested in, you can forget. I'll just recap everything at the end of this first part, and just focus on the things which are important for the next parts of this talk. So what we are studying here, from the physics point of view, is cosmology. It's a cosmological model, which is the theory of a conformally coupled scalar field, which I call phi here, which is conformally coupled, which means that there's some metric on a space, and it's coupled to gravity in a very particular way. And it contains, so this theory also contains some non-conformal self-interactions of this field, which can be any polynomial interaction where these polynomials can be trivalent, but also higher order interaction terms. And we will focus here on the so-called power law FRW cosmology, which means that the metric on that space will depend on a scale factor, and this scale factor, is a function of time or conformal time in that case, and in power law cosmology, it will be a very simple function. So there is a simple function which just determines how the universe expands, and it's a very simple one. It's just the time to some power. And depending on what power we take, we talk about various different cosmologies. If the power is equal to -1, literally when this is a constant, then it's a flat space. So that's something very simple. If epsilon is equal to 0, that's the de Sitter space. When epsilon is close to 0, it describes inflation. Okay, and so in this theory, so again, it's a conformally coupled scalar field, power law FRW cosmology with this action. What we want to discuss and describe is some correlation functions, and some correlation functions of boundary fields. This field phi here. What I can do, I can take a boundary field. So our space, I choose some time equal to 0 surface in that space, and just try to take the small phi field evaluated there, so the time equal to 0, and I want to calculate correlation functions of such field. So the correlation functions are just given by some path integral with some function here, which is called the wave function of the universe, which just determines, it's the most important thing which we want to calculate. And this wave function can be calculated in the Fourier space just by the formula here. So what it's given by, this psi n, small psi n, which is a function of momenta. So these are momenta on this t equal to 0 surface. And so these are three-dimensional momenta in that case. And what we want to calculate, we just want to calculate what this so-called wave function coefficients are. Okay. And in order to calculate it, so this is a picture which we can plot. So we can use here. So we have the surface of constant time, so t equal to 0 conformal time, and then our fields there, and we want to calculate the correlation functions of these fields. So there's coefficient here. Phi n just tells us one of the contributions to this wave function coefficient for the wave function of the universe, and it depends on this momenta. So this is a quantity which looks quite similar to the things which we calculate in scattering amplitudes. It will depend on momenta. In that case, it depends on 3 momenta, not on 4-dimensional momenta. There will be no conservation of energy here, but quite a lot of things which we study here are similar to scattering amplitudes. In particular, what one can do, one can calculate this quantity using the standard Feynman approach. So one can translate this action here. One can find particular transformation of this action such that so one can derive Feynman diagrams for these quantities. And the Feynman diagrams are quite easy. So what you need to do, in order to find this quantity, you just need to expand over all possible graphs. And each graph will contain, these are graphs which have some number of vertices at the boundary, which is equal to the number of fields which for the correlation function which we want to calculate. And we'll have some number of vertices in the bulk. And we have some bulk to boundary propagators, and then bulk to bulk propagators, and some interaction vertices here. And what we need to do, so there are expressions from that action. One can derive the expression for all these terms. So to each of such graphs, we can associate an algebraic expression, algebraic function, which we would actually calculate. In order to find all this, in order to calculate this wave function coefficient, we need to sum over all possible graphs. And there will be some graphs which, when I remove the bulk to boundary propagators, which are common for all of these graphs, and only focus on the things which lives in the bulk, there will be some graphs which are like this one, which is a free graph, but there can be also loop graphs and so on, like higher and higher number of cycles and more complicated. So in this theory, as I said, we don't specify what is the so in this action here, we can have interaction of any degree. which means that this vertices here can be of any size. Okay, so now what we are interested in just calculating each of these graphs separately. So just find an expression for it and just evaluating it explicitly. Now, if we do that for flat space, that the result we get is just a rational function. If we do that, so the flat space in that case means, again, when this epsilon is equal to -1, so that's the simplest possible example of this theory. But we would like to calculate it also for any epsilon, and in that case, these functions which we find contain some integrals, as I will explain this. Okay, so we would like to find these expressions for any epsilons or for any of these cosmologies, FRW cosmologies. The important thing is that when we calculate these expressions, then as I said, we can forget about the dependence of the boundary to bulk propagators and only focus on the bulk pictures here. And all these expressions will only depend on some particular combinations of momenta we are flowing in or flowing out from through each of the vertices. So what I can do to each of such graph, I can associate some number of variables, let's call them coordinates, where to every vertex I associate x's, and to every edge in this graph I associate y's. And x's are just sums over all of the momenta, the external momenta, which are flowing in. And y's are just the norms of sums of momenta which flew into this particular vertex. Okay? So everything will depend on xv and ye for every vertex in this graph and for every edge in this graph. Yes?
Can you say what y is again? I didn't quite follow.
Say again?
Can you say what y is again? I didn't understand.
The y. This?
Yeah.
I mean, you just take, so for example, in this case, you have some momenta which are flowing here, so some external momenta. So you just take the sum of them. So there's a conservation of 3 momentum here, right? So the momentum flowing through that edge is exactly the sum of the momenta, right? And then you just take the norm of it, so it's like energy. Okay. So the important thing from here is that it only depends on these variables x1, x2, and y12 in that case, and then for more complicated graphs, there will be some number of variables associated to vertices and some number of variables associated to edges. Okay, so as I said, for the epsilon equal to -1, that's the answer which one finds is just a rational function. But if you want to find the expression which is valid for any epsilon, then it turns out that there is a very simple formula which relates what I call the flat space function with the one which I want. So in order to do that, what I need to do, I need to just integrate the flat space wave function from 0 to infinity over all. So first of all, I need to take it and to shift it by some. So all the variables associated to vertices are shifted by some new integration variables, and I need to integrate them, and I integrate them with some prefactor, and this prefactor is this x to the v alpha v, where alpha v depends on. So each such term corresponds to one of the vertices in my graph, and alpha v depends on epsilon, so which cosmology I take, and it depends on the what type of interaction I have. So how many incoming particles how many incoming edges, how many incoming lines I have in my case, in my vertex. Okay, so what we would like to do, we would like to just calculate these coefficients as functions of xv and ye, and in order to do that, I just need to evaluate these integrals. So that's in principle, I mean, it's quite a complicated thing. Even if I know how to find this rational function, which I explain in a second, doing these integrals is quite difficult task to do. And just to kind of introduce us to the notation which I will use later, I can rewrite the integrand of this integral in a very particular way, where I combine this dx, so the differential part, with the psi flat. I call it omega flat, and that will turn out to be a logarithmic differential form. And then there will be this factor u here, which is just the product over all vertices, xv to alpha v, which is just giving me some, as we'll see in a second, this gives me some kind of regulator of this integral, but I will call this U at least. Okay? So this kind of integrals, they fit into a broader family of, broad family of integrals. They're called twisted integrals. So where U is a twist, and we integrate over some domains or some contour a differential form, which is like okay. So in order to do that calculation, we can proceed in various different ways. So first of all, we need to know how to find this flat space functions, the rational functions, and there are various ways how to do that. First of all, we could just use direct Feynman calculation, so just associate it to every graph using Feynman rules, a Feynman expression, and that would give us an answer. But there are some shortcuts. So for example, Nima and Paulo, I forgot the name of Postnikov. I'm sorry, Postnikov, just found the same function just using cosmological algorithm. So if you are familiar with that, then they gave a prescription, which is quite combinatorial, and I will kind of explore it here later on. And also together with Ross, we gave a different way of calculating the same quantity using so-called some functions which we call amplitudes, which are also introduced. Okay, so that's step one. So step one is to just find this function, but step two is to integrate this expression. So that's end of physics. So from this part, what we need to take from this part is that in order to calculate quantities which we are interested in, so we are interested in wave function coefficients which depend on a graph. So we need to fix a graph. For every graph, we'll have a function which we want to find. More general case, with some transcendental function, depending on various parameters, this alpha v are parameters, and depending on the kinematic encoded by the coordinates xv and ye. And so what what I said, after we fix the graph G, what we want to find, we first want to find the flat space wave function, which is this rational function, using one of the methods which I explained before, or alternatively a logarithmic form on some positive geometry, which encodes the same information. And then what we want to do, when we find this canonical form, we want to integrate it, so using this twist integral, just integrate it and find the answer. So the answer is the wave function coefficient associated to my graph G, and it is a function of kinematics of this problem. So the xd and ye contains all the information about the kinematics. Okay, so these are the steps of our construction. We will not do the integral directly, so that is a quite difficult problem. Instead, what we'd like to do, we would like to find some differential equation which this integral satisfy, and then when we find the differential equations, we would like to solve them. So as a next step. So this is, if you are familiar with the development in Feynman integral calculations, that's also the direction which people there took. So we would like to do the same. So we would like to find some differential equation. In order to do that, we first, so this expression here, which just corresponds to this omega g, so the canonical differential form of some positive geometry. What we do, we'll expand it into some basis of basis of forms, a natural basis of forms, which will be labeled by tubings of the graph, which underlies our problem. Okay, so I'll explain what tubings are in a second. Some particular tubings, the various definitions, and we take we need very particular one. When we do this decomposition, what we can do, we can just decompose our function. So this function here, if we can decompose the integrand, we can decompose our function and introduce new functions which are just twisted integrals of this basis differential forms labeled by tubings. Where again, here U is the twist, and I will tell you later what this omega tau is. And then what we'd like to do, so these functions, all of these functions, and also the functions we're looking for, so the FRW wave function coefficients, they depend on the variables xd and ye. So what we can do, we can introduce a differential which acts on that kinematic space, And so this is just given by this simple form here, where the sum goes over all vertices and all edges of our graph. And then what we really want to do, we want to find what is the result of acting with this kinematic differential on our wave function coefficient, but that usually produces some additional functions on the right-hand side, so that's not immediately straightforward to find. Instead, what we find, we first act on this with this kinematic differential on our set of functions, and this turns out to be a closed set of differential equations, linear differential equations, where this matrices B are some matrices. And these alphas are just as I said, the parameters which are associated to each of the vertices in our graph. Okay, so when we find this, because we have the expansion of the integrands and therefore the integral, this integral in terms of functions f, if we can solve this equation, this set of equations, we are able to find the answer for the wave function coefficient as well. Okay, so I will stop here. So I will not give you the solution because that's a difficult problem which we are working on now. But the next step would be you write the differential equations, you want to solve them, and then when you solve them, you just So if you solve them for f, you can just assemble them back into the functions which are really interested. Okay, so this will be our steps, and I will do the first three and not the other two. Okay. So now we are not the first people who are trying to do that. There are at least two other approaches to this problem, and we are quite new to this problem, but we think that we can add something to the constructions which already exist. So there are these two constructions. One of those goes under the name of kinematic flow. It's a group of Daniel Baumann and others, with some papers which were published very recently. Their method is based more on physics than on what I will explain, on the combinatorics which I'll explain today. And so their description is based on some physics fact that the back-to-back propagator can be decomposed into three different pieces, and they use these three different pieces in order to this expansion here with some different bases. However, in order to do that, they have some combinatorics in that problem, but this combinatorics requires the graphs which are introduced. It requires to introduce additional dressing of these graphs. It doesn't seem to be very natural from the point of view of the underlying graphs. So we would like to improve on that. And then there's another approach which is based on twisted cohomology, that's Shonak and Andrzej. And they work in cohomology theory of arrangement of hyperplanes. I'll explain what these hyperplanes are in a second. What they are lacking, in our opinion, is that this arrangement of hyperplanes does not know nothing about the physics, and just gives you too big set of basis functions, and therefore choosing a natural set from the point of view of physics is just not straightforward there. Okay, so this is something which is physics based. This is something which is maths based. We want to fit somewhere in between, but improve on both of them, as I try to argue now. Okay, so in order to explain the story, I need to go through this. I need to explain what the combinatorics is, and then I need to explain what the geometry is behind this problem. So I start with combinatorics. As I said, every quantity which we want to calculate is related to some graph. And in order to do the decomposition of the wave function coefficient for a given graph, I need to find a basis of functions, and this basis of functions, in our case, will be labeled by tubings. I will introduce three types of tubings. This is required in order to, for this construction to really work. So one of them we call B tubings, the other U tubings, and the C tubings. It's like binary, unary, and cat tubings. So that there will be three different names for them. So I start from the simplest one. So for me, I want to define what B tubing is. So let me start from defining what a B tube is. A B tube is, if I take a given graph, a B tube is just a connected subgraph. Okay, so if I have a graph, I have some number of vertices and edges, And if I remove some number of vertices and edges and the result is connected, I call that a B-tube. Okay, so this is a particular example. So the black is my graph. It's a graph with 2 vertices and 2 edges. And for example, I can take a subgraph which is just surrounded by this blue tube. And that's a subgraph which contains these 2 vertices and just the edge below. That would be a B-tube. There will be more B-tubes here. I can just take, for example, just a single vertex. That's already a connected subgraph. Now, in order to visualize connected subgraphs, I will be just drawing these tubes around. So these tubes just tell me which vertices are inside of my connected subgraph, and so they surround, they encircle the vertices and all the edges that are inside. Now, for a given B-tube, what I can do, I can introduce a tube function. So remember that to every vertex I associated some x variable, and to every edge I associated a y variable. I can define a function. So what I'll do, I will just take the sum over all x's inside of the tube, and all edges which go out from a given vertex, which are kind of removed. So I started with my graph G, I removed some edges, and I sum over all of those which I removed here. So in particular, if I take a path graph with 3 vertices, so that's a path graph with just 3 vertices just connected like this, like a ladder. One of the B-tubes is just a tube, just a subgraph containing the first vertex and nothing else. In that case, the function which I associated to it is just the sum over all the vertices inside, which is just the vertex 1, so x1, plus all the edges which are in the original graph, are attached to this vertex, but are removed from it when I take the subgraph. Okay, so these are the six B-tubes which I can define for this particular graph, and then 6 functions which I associate. Okay. So that will be important later, because these are exactly this equal to 0 will be exactly the equations of hyperplanes, which were used, for example, in the hyperplane arrangement in this homologic approach. Okay, so now if I have tubes, so I define tubes on a graph, I want to define compatible tubes in order to define tubings. Okay, so I say that 2 B-tubes are compatible if one of 2 things happens. Either they're nested inside of each other. So if they're nested, it means that one is strictly, it's a subset of the other. So like in this case. Or they are disjoint. So the second example is of tubes which are disjoint. So there are 2 types, two scenarios in which I say that tubes are compatible. And then if I know what compatible tubes are, yes? Sorry. I can define B-tubings, and B-tubing is just a collection of compatible B-tubes. Okay, and then I can also define a maximal collection, maximal B-tubing as a maximal collection, so I cannot add any more B-tube to that. So in particular, if I take the start graph like this, these 2 tubes are compatible, so they form a B-tubing. And if I want a maximal B-tubing, I need to add more compatible tubes, and all these tubes in this graph are compatible. As you can convince yourself, they are either nested inside of each other or they are disjoint. Yes?
What does maximal mean, sorry?
Maximal means that I cannot add any more compatible tubes.
Yeah.
So to this picture, I cannot add any more because they would start to cross. Okay, so this is one type of tubings which I will use. The second type is called U-tubings. So a U-tube will be a connected subgraph generated by a subset of vertices. So in that case, instead of removing some number of vertices and edges, I just take a subset of vertices and all the edges in the original graph which these vertices were connected in the original graph. And if that's a connected subgraph, then I call it a U-tube. So a U-tube, for example, this is a U-tube because I can choose these 2 vertices and all the edges in the original graph which were connected, which these vertices were connected by. But this is not a U-tube because if I take the subset of these 2 vertices, then I need to take also all the edges. So that is a B-tube, but that's not a U-tube. So in particular, there's a statement that every U-tube is a B-tube, but not the other way around. That's easy to used. Okay, and then compatibility of YouTubes is slightly different. It's similar but different. Two YouTubes are compatible if they are nested. So these are again compatible YouTubes. But if they are disjoint, they cannot be adjacent. Okay? So what does it mean that two tubes are adjacent? If I take the two disjoint tubes such that their sum, so the union, is also a U-tube, that's not allowed. Okay? So in this case, if I took these two tubes and they took their union, in that case that would be a U-tube, and that's not allowed. So this is not compatible U-tube. So that would be compatible B-tubes with U-tubes. Okay, and finally, so now U-tubing, the definition of U-tubing is exactly the same as before. So if I take a collection of compatible U-tubes, I have U-tubing. If I find the maximal collection of U-tubes, maximal collection of U-tubes, it's called maximal U-tubing. So in that case, for example, this is U-tubing. I have one tube here and the big one encircling all the graph. And this is a maximal one. And as you can see, there's less tubes here. So it's the same graph as before, which I explained. So this was the maximal B-tubing. You can calculate how many tubes there are. There's 4, 5, 6, 7, which is, by the way, the number of vertices plus the number of edges. But the maximal U-tubings, they contain here 4 tubes. This is just the number of vertices. So there's, for maximal tubings, the number of maximal tubes in U-tubing is equal to number of vertices, and for B-tubing, number of vertices plus number of edges. Okay? And I emphasize this external tube, which just encircles all the graph. So, of course, the graph is a connected subgraph of itself. So that's also a U-tube, because I want to give a special name to it. I want to call it the root, and it will be important in a second. So for example, if I take the path graph, so again, a graph with 3 vertices, I can list all possible U-tubings on that graph, and there will be 1, 2, 3, 4, 5 maximal ones, and there will be some non-maximal ones, and 5 of them, and then this one contains only the external one. I want for U-tubing, I want the root, so the external tube always present there. The root is always part, I define U-tubes, that the root is always part of the U-tube. Okay, and finally, the C-tubings are just a combination of these two notions. So what I need to do, I need to take my graph, G. Let's take the star graph. And first, what I want to do, I want to remove some subset of, this should be edges. So subset of edges, like I did here. And I can remove any subset of edges. And if I do that, then the resulting graph, you can think about this as, so if I take all the connected components of this graph, every connected component is a B-tube. So in that case, there's 3 B-tubes here, so as I indicated here. So there are 3 B-tubes. So every time I remove edges, and just look at connected components of that graph, I can define a B-tubing on that graph. Okay, so removing edges is equivalent of defining a B-tubing. And then C-tubing, or equivalent to maximal C-tubing, is taking this B-tubing and just further, so in every of the roots, I can introduce, I can put additional U-tubes such that for every disconnected component, I get a U-tubing or a maximal U-tubing. Okay. So that's the definition of what a C-tubing is.
So are you moving a subset of edges?
Edges, yeah, I'm sorry, that's a typo. Yes, that's a typo. Yeah. Okay, so for example, if you want to look at C-tubings, all possible C-tubings for path graph, then they are kind of divided into various classes of C-tubings. I can take my graph and don't remove anything. In that case, I just reproduce the U-tubings that I had before, because what I need to do, if I don't remove anything, that's a B-tubing with the B-tube, which is just encircling everything. And then as I said, after I remove some edges, I need to just take all possible U-tubings inside of all the connected components. There is one connected component, so just one set of U-tubings here. So this exactly reproduces the previous 11 count which we had before. But then I can remove this edge, and in that case, the B-tubing which I get contains these two red B-tubes, and then I can put more U-tubes inside such that it is compatible. So in that case, I can put either a U-tube around the first or the second vertex, or none at all. Okay, so that's another C-tubing. Or I can remove this edge here. In that case, I have another three of them. Or I can remove both of them, and this is the only C-tubing. Okay. So that's 18 of them in that case, which is an important number. Okay, so that's end of my combinatorics part of this. So what I wanted to introduce, the notion of C-tubings, because they will be labels of the functions which will be relevant to our problem. Okay, so hopefully the definition of C-tubing is clear. Okay, so now that was combinatorics part. Now let's move to geometry, because geometry, what geometry will give us, it will give us an explicit expressions for the flat space wave function coefficients, which are just rational functions. And it turns out that there are to each such wave function coefficient, I can associate a positive geometry, and that the canonical form of this positive geometry will exactly contain this wave function coefficient as I explained in a second, as explained in the next slide.
Sorry, John, can I ask, what do B, C, and U mean?
Yeah, so B is binaries, U is unary, and C is cut, because you cut the edges. It is a notation which was introduced by Ross Glue in his paper, and just took it. Yeah. So I think that the U-tubes and U-tubings are the ones introduced by Devados. So I think that these are the most, and Carr, these are the most familiar to mathematicians. And B-tubings and C-tubings, so B-tubings is, I don't know if there's any literature on that.
Yeah, we did.
Very good, very good. So I'm sorry about that. Yes, so I'm looking for.
Too.
Okay, yeah.
I'm going to talk with them about it.
Okay, so that's great. Yeah, so I was not aware of that. I think there's a lot of tubings on graphs.
Okay, was that B or C?
The B ones.
The B.
They're sort of the simplest ones in some way.
Okay.
Yeah. And then C-tubing is just combination of two of them. I apologize for not saying. Okay, so in order to tell you how to find this wave function coefficients, what I introduce first, I will introduce a notion or a function which can be defined on any graph, which we call an amplitude, because it is something which is very similar to phi cube amplitudes, so trace phi cube amplitudes, but can be defined on any graph. Okay, so the phi cube in this story, phi cube story somehow fits in when you just take path graphs, so graphs with just kind of ladder graphs. But it is possible to extend this notion of the expressions which you can associate, which calculate the amplitudes for the path graph. This is possible to extend to any graph. So how do I do that? I define an amplitude for a given graph that will be connected, just for simplicity, as a sum over all maximal U-tubings. Okay? And then what I do, I take the product over all tubes in that U-tubing, and then take inverses of the functions. So this the tube functions which I associated to every tube. Okay, so for a simple example, again, path graph with 3 vertices. We said that the number of maximal U-tubings are 5 of them, and so what I need to do, so each of these terms in this expression corresponds to one of the maximal U-tubing. So for example, if you look at these 3 expressions here, I combine these 3 tubes, that's a maximal U-tubing. And I need to take sum over all maximal U-tubings and product of inverses of these functions h, where the expressions for h were given before. So let me just tell you once again. So these are the expressions for all of them. So they're just linear expressions in x's and y's. Okay?
Sorry, this is maybe a silly question, but it's important before we continue. You call this an amplitude to be cute, right? Because this is also literally the amplitude, or is there some subtlety I'm missing?
It is amplitude if the vertices, sorry, if the graph is a path graph.
Ah,
But yeah, so that would be phi cubed, trace phi cubed
Right,
amplitude.
yes.
But if you take the graph to be something else, that's
Sure.
that's not, there's no relevance to physics of phi cube or other scattering amplitude physics, right, which I know of. But still, there's a very meaningful set of functions which you can associate to every graph now. And these graphs are not only they're not only three graphs; they can have cycles as well. So you can do that.
Sorry. So, I mean, these maximal U-tubings correspond to faces of the graph association, right? Maximal faces for.
Yes. Yes. That's true. Yes. Yeah.
Okay, so your canonical form, like usually you would sum over triangulation, over pieces of a triangulation, but here is sum over facets.
No. The maximum U-tubings are vertices. They are vertices. Yes.
Okay, sure, vertices. But at the bottom you have a sum over all vertices of these at the very bottom of the slide.
Here.
Yeah. But
The sum is still over the vertices.
okay, so sum over vertices of some wedge of D log. So
These are facets. Yes. You can think about this as a facets.
yeah, I've just never seen this before. I mean, like, is it true for any polytope that the canonical form is a sum over vertices of D log of facets?
No, that's not true. I think that's beyond that. So for simple polytopes, it's always true.
Oh, it is? Okay.
Yes, with the caveat that there's realized signs here in front. So I cheated a bit here because I didn't tell you how I ordered these D-logs, right? But there is a canonical way of ordering these D-logs so that the signs disappear. But for simple polytopes, it's always possible. Our polytopes will not always be simple, but in that case, if you look at the paper of Francis Brown,
Polytopes should be simple.
no, I explain why not. Yeah. So if you look at the recent papers, which was already mentioned, Francis Brown and I forgot the other person, they also give a prescription for polytopes which are not simple. And you sum for every vertex which is not simple, you sum over some circuits, broken circuits, I think. So in that case, it's also a sum of over vertices, but for every vertex you might have more than one contribution. Okay. So what will happen here is that this maximal U-tubings, there will be more than one maximal U-tubing which correspond to the same vertex of this graph. So I wrote here degenerate for a reason which I explain in a second. So that's true. So if this H were just generic, that would correspond to the case of the graph-associahedron. So each of these terms corresponds to a vertex of a graph-associahedron. But you need to remember that this H, the way I wrote H, they depend on these other variables here, x's and y's. And there are some non-trivial relations, I think that was in paper of Mark and Anastasia. There are some non-trivial relations. For example, if you take this tube plus this tube is equal to this tube plus this tube. Okay, and this will generate a situation where, so there are some relations between facets, and that will introduce simple vertices in the construction. So it turns out that, just coming back to this description here, so the amplitude is given by this expression, but when H is given by the tube functions which I gave you before, that will correspond. The amplitude can be extracted from the degenerate graph-associahedron, not from the graph-associahedron itself. Okay. So how I define this graph-associahedron, or degenerate because they're not the same as the ones introduced. They're defined as we just take all the tube functions to be non-negative. Okay, so this this is a polytope in a space of, and I treat this polytope as only living in a space of x's. I treat y's as coefficients, but this will just live in a space of x's. So the number of dimensions in which this polytope lives is the number of vertices in my graph. Okay, and then we so if I do that construction, this is a positive geometry with canonical form. The canonical form will be just the sum over all maximal U-tubings of d logs of the facets of the vertices. I mean, given by the tubings really. It will be proportional to the amplitude. So I can extract the amplitude. If I just drop the top form part, then the coefficient in front is just the amplitude. And this is just to illustrate that it's not true that it's not really a hexahedron which we get, or graph as hexahedron, but there are some degenerations which happen. So if I take again path graph with 3 vertices, I would expect to get an hexahedron in 2 dimensions. In this construction, there's something which what it really gives. It gives us a cone over that hexahedron. So it's really a 3-dimensional picture where this facet here is this facet x1 plus x2 plus x3 equal to 0. And the other 5 ones are 1, 2, 3, 4, and 5. Okay, and then it goes to infinity. So it's a non-compact object. But it's not really a hexahedron. It has just 4 edges and 4 vertices because this so the front one and the three facets here, they intersect at a single point. Okay, so from the pentagon, it just reduces to a quadrilateral. Okay, so in that sense, it's degenerate, and the degenerations can be much more severe when we go to more complicated graphs. Okay, but why did I introduce these amplitudes? Because if I now can construct amplitudes for any connected graph, there's an expression which can be found in far spaces, but mostly in Ross's paper, how to write the flat space wave function coefficient in terms of amplitudes. So in order to do that, so for a given graph, the flat space wave function coefficient is given by a sum over all possible subsets of edges. So I take my graph and start to remove edges, 1, 2, 3, and so on. And then when I do that, the resulting graph has some number of connected components, and I just take the amplitudes, so the product of amplitudes on this connected component. Okay, so the objects which we want to find in the flat space, so the rational function which we want to is a starting point for our construction, is just given by sum over all subset of edges of my graph, product of all amplitudes on connected components. So in a simple example, again, in order to find this one, what I need to do, I just need to start to remove some edges. So I don't remove any edge, that's the amplitude just for the path graph with 3 vertices. If I remove one of the edge, the second edge, then the product of the amplitude on the first 2 vertices times the amplitude on the third vertex. So the red one indicates which amplitude I'm taking. And the same here. And then if I remove both vertices, then there are 3 connected components, and it's a product of 3 amplitudes.
Should it be plus?
No, and I'm sorry. Yeah, this should be plus. Yeah, thank you. Yes, that should be plus. It's an alternating signs. Okay, so this is a similar story for differential forms. So now, as I said, every amplitude corresponds to some positive geometry. It's a cone, and it goes to infinity. But it's a very interesting thing. If I combine with these expressions here, they originate from some geometry, which turns out to be more, at least in the cases which we studied, it's bounded, and it usually is some collection of polytopes. It's a very strange collection of polytopes, and I will come back to that in an open question session, maybe to give you some examples. But the point is that what one can find the psi just by summing over some degenerate products of degenerate graph. Okay, but then if you think about the definition which I introduced before, this expression is exactly can be rewritten as a sum over all maximal C tubings, and that's the reason why I introduced the maximal C tubings, because the flat space canonical form or a function which I want to study can be written as the sum over all maximal C tubings with some signs, sigma tau, and the product of all of the logs of all the tubes in a given C tube. Again, with some particular ordering, which we understood quite well, which allows the sign to be, the simplest possible. Okay. Good. So far, what we managed to do, we managed to find that the flat space wave function for a given graph can be written in terms of products of amplitudes or sums of products of amplitudes for subgraphs of this graph. Yes?
Please ignore this question if it's incorrectly asked. But in your example, like you had this thing that was like a degenerated pentagon.
Yes.
But there's still a notion of the various pieces being connected one next to each other as you go around. So is there an operation that's like mutation of a tubing into another tubing that's adjacent to it?
Very good. This is my open question number 4. So I don't know what is the relation to any computational cluster algebra, but I will show you some examples where there's a hint that there might be some cluster algebra behind. But I don't know the answer to that. But it's part of my open question. Okay. So far we have we have this expansion, and therefore what we can do, we can because we are looking for this FRW, so not the flat space, but FRW function. We just take the thing which we found from the amplitudes and just calculate the twisted integral of it. So this is the thing which we would like to now find. And this just is one of the family of twisted integrals, which are, again, it's a very particular twisted integrals because, U is a twist which just takes all the coordinates or the integration variables to some powers, but omega is very particular. It's a logarithmic differential form on some particular space. Okay, so now this is just to show you. As I said here, this can be written in terms of the maximal C tubings. But in a second, what we'd like to do, we'd like to construct these functions f, which are the twisted integrals of these expressions, and we would like to act with the kinematic differential on it. And when we act, on the right-hand side, we would like to recognize what we get on the right-hand side, and we would like to make sure that the things on the right-hand side also are part of our basis, right? So we would hope that if we act on any of such twisted integral of such differential form, on the right-hand side we still find twisted integrals of the differential forms of the same type. But it turns out to be not the case. We need to slightly modify this expression, and a more natural set of or bases, maybe quotes here, of differential forms, which are natural from the point of view of the tubings and from the point of view of this action of the differential operator, is slightly modified. Instead of d logs of the numerators here, we need to modify them such that we divide each of the elements by the coordinate axis. So x1, x2, up to x number of vertices. So this turns out that now if you take this, first of all, the flat space wave function, so the thing which we are interested in, can be expanded also in these functions, but in that case, instead of the summing over all maximal C tubings, we need to sum over all C tubings. Okay, so it's the same formula as before, but instead of maximal C tubings, we have just all C tubings. Okay, so now what we want to do, what we accomplished already, we managed to expand our FRW function, which we are looking for, in terms of some tubings, or functions associated to tubings, and we know now which tubings we should take, and how these functions are defined. So this f tau are just the f tau are just the twisted integrals of these canonical forms. Again, this is a canonical form of it's not anymore graph associahedra, but there are some polytopes which are very easy to understand. If you just look at this, stare at this formula, it's very easy to just identify it in the space of in that case, this small axis, what these polytopes are. Okay, so this accomplishes step 1 and step 2 of our construction. Now what we want to do is to take...
Sorry, can I see if I understand? So you're replacing each big X with a little x plus a big X?
Yes, so we make a shift. So that the formula for the function which we want to find really is that we need to take the flat one and then just shift and integrate over the small ones.
Okay. And before the variables were big X, and now the variables are little
Yes.
x?
So yeah, I should be maybe more precise. So when I talk now about differential forms, I need to tell you what the differentials are acting on. But because everything is a shift from capital X to small x, then I can just move the differentials. So previously there were forms on the big X and big Y, but I can think about them as differential forms on small x, and they will satisfy all the same properties as previously. Okay, so now what I want to do, I want to, again, just to recall, I take this kinematic differential, and I want to take it and act on the functions which I found, on my basis of functions, and see what happens on the right-hand side. And I hope that what I'll find that this system closes, which means that all the functions on the right-hand side are one of the functions which in my basis here, with some matrix B, and this matrix B will depend on the exponent of the twist, so these are parameters of our story, and they will be really, the entries will be just one forms in this x's and y's, and they really are differential logarithmic one forms. Okay, so additionally what we want to do, so if you follow the story of the differential equations for Feynman diagrams, what people wonder is that the matrix B to be such that if you take the parameters in your story to 0, that the matrix goes itself to 0. If that's satisfied, then solving this differential equation is easier because you can do this perturbatively. And in that case, the differential equations are called canonical. So what we'll find here that, that's the case, that the differential equations which we'll find here will be canonical by some very simple argument.
Can you just go back to the differential equation itself?
Yeah, so this B really is alpha 1, B1, and so on, sum over all vertices. And then just to say that the statement that, this differential equation here, because of the form of our basis, is equivalent up to total derivatives to a statement really on differential forms. So what I can do, I can just do the differential, kinematic differential of the NA omega, and what I'll find that this is just the B wedge omega. So it's the same B as before. As I said, B, the entries of B are logarithmic forms, so I need to put wedge between them. Okay, and the important thing is that, just to emphasize that what we ended up with for our basis, all of our forms are logarithmic, so they're always of this form, d log of some function, or wedge d log of some other function. Okay, so what we would like to do, we'd like to derive differential equations. And the argument which I present here does not rely so much on the explicit form of the forms, of the differential forms which I introduced before. It's very general, and at least for this type of twisted integrals, could be applied also in other contexts for other differential forms, or twisted integrals of of logarithmic forms. So what I want to do is a simple algebra here. I want to add with I want to take any function f, which is a twisted integral, so given by some twist times logarithmic differential form. I want to add with d king on it, so the kinematic derivative. I can just bring this inside. Then it will act on the twist and on the omega. I can do integration by parts, which is a trivial integration by parts if omega is logarithmic. Which tells me that the kinematic derivative on this omega is the same as a normal derivative, so the derivative with respect to integration variables of some other omega tilde, which is just given here. So that's a simple algebra to do that. This is the only place where I use integration by parts. And if you know something about the story for the Feynman diagrams, integration by parts is usually the most difficult thing there. In order to find the basis of functions which are interesting, and in order to do any calculations. So here, I want to emphasize that the integration by parts plays, it's realized in a very, very simple way. Okay, And because of the twist, the boundary terms just drop. And what I get at the end, I mean, if I combine all these things, I get that acting with the kinematic differential on my function on the twisted integral just gives me a twisted integral again with the same twist, but of a different form. This form now, so I introduce this capital D, so the D is just the sum over two of the derivatives. So somehow what I can do, I can just think about the kinematic space and the internal space, so the integration, the space over which I integrate I can combine them together, introduce new derivative which just takes into account all the variables, and do the same with omega, so just uplift the small omega which I had before, just replacing the small d by the capital D, and the action of the differential equation on my function is just very simple. It's again the twisted integral with the form, which is very easy to write. It's just d log u when you use the twist with the omega, which is this uplift of small omega to the big differential form. Now, by doing this, I added a lot of zeros to this problem because on the right-hand side now there will be these forms here. We have various degrees in d kin and d, but the integration sign, I know what is the contour of integration, just always select for me the proper degree form in the integration variables. So there's a lot of zeros which I added here, but by doing that, I made it very, very symmetric and simple to write explicitly. And this works for any logarithmic differential, twisted integral of the differential logarithmic form. And then just using a very simple relation which calls for logarithmic differential forms, if I, there is a d log missing here, if I take the logarithmic differential form, I can always take any sum or difference with plus or minus 1 factor in front, and combine any number of functions inside of the d logs, and it turns out that this differential form is equal to d log of the sum or difference with some d logs of the ratios of the alphas. Okay, and I need to do that because notice the following thing. So now here on the right hand side, now what I'd like to do, acting with the differential operator, so that this d kin on my function, I got some I got some differential form here, but then what I would like to do, I would like to now, so this is a differential form of order degree omega plus 1, and I would like to now decompose it into the basis of my omegas, which are of degree omega, and wedge something which does not depend on integration variables, because then I can pull one of the differential forms in front of the integral, and then the rest will be one of the twisted integrals of the basis which I had before. So in order to do that, I use this relation here. If you do that, then it turns out that you can always rewrite the expression before such that one of these elements, one of the d logs in that expression, does not depend on the integration variable, and the rest is one of the omegas in our basis, which allows me to just take this and pull it outside, and the rest is just one of our twisted integrals in our basis. So this is always possible just using a simple relation. What turns out is that the d logs which I get here, so this will be the coefficients of or entries in our B matrix. So this the arguments of this element here are they have very simple and interesting combinatorial interpretation. They're just something which we call region variables. So it's one more about region variables, and I give you an example, and then I conclude. So what are region variables? These are variables which I can associate to regions in the tubing. So what is a region? By region, what I mean is a collection of tubes which contains one parent and children inside, so subsets of this parent, which are, there may be many children, but the point is that if I have more than one, then they need to be disjoint. Okay, so this is an example here. So a region which contains this parent and this child satisfies all these properties, and I can associate to, this is a collection of tubes for which I will depict like this. So I can think about this as a region between the parent tube, which is this tube, and the child tube, which is the smaller tube. And I can associate to that an expression just by taking the tube variable for the parent minus the sum of the tube variables for all the children. And I get that particular case, the region variable for this region is just given by this. And the region variables are really letters in my differential equation. So for this problem, this will provide me letters. So this brings me to, this will bring me to the question about cluster algebra in a second. Okay, so just to give you a very, very simple example, so we can do that very, very explicitly for many, many graphs, as long as our Mathematica runs. If you take path graph, this is it depends on 5 variables now. 3 of them are vertex variables, 2 of them are edge variables, and for that graph, I can define all the C tubings. So this is, if you remember, the flat space, the canonical differential form is written as a sum of all C tubings. There's 18 of them. So this is an explicit expression with all the C tubings written explicitly, where this mu were given in the, I gave the expressions for them here, but now I can write some of them explicitly. So for example, the mu for this tubing is just given explicitly by this an explicit form, where I use this capital D. As I said, I can go easily between the capital D and the small d, because the integration contour selects for me always the appropriate degree of the form, so I can uplift everything to the capital D, so on this bigger space which contains the integration space and the kinematic space. So these are 2 examples of the canonical forms of polytopes which are relevant for this problem. And then this is, I just give it to just illustrate what kind of expressions we can get. So just forget about the second part for a second. So if I want to act with the, when I act with the D kin on F, it's the same, as I said, it's the same as acting with D log U on our canonical forms. And I can write this action very explicitly. So if I act with D log on, let's say, this function corresponding to this tubing, on the right-hand side, I just get some sum with coefficients alpha 1 up to alpha n, alpha number of vertices, some letters, so D logs of some letters here, wedge the functions which I have before, some of the functions in our basis. And we understood very well what the pattern is, so I'll tell you in a second what the general formula is. But the important thing here is that all these D logs in front, so the elements of this B matrix, which is important for the, which gives the coefficients of the differential equation, are related to this region variable. So I indicated all the region variables here with the shaded areas. Okay, so this gives us the equations where everything lives in kind of the same combinatorics, where the functions are labeled by tubings, C tubings, and the coefficients of the differential equations are labeled by these region variables, or D logs of the region variables, for the same tubings, for the same notion of tubings. Okay, more general, if I now do that for any G and for any C tubing, this is kind of schematic form of the answer. It will be always a sum over vertices with these coefficients alpha v, and then it will be sum over some regions, which are specified. If you look at this answer here, you can probably recognize already what kind of patterns emerge. We know exactly what this sum runs over, and then for every region there is some sum over the basis functions which we had. So there's some sum over C tubings. Okay, so I don't give explicitly what this R and T are here, but there are some very well understood subsets of regions and tubing. So this gives you the answer for any graph. And this is a purely combinatorial formula now. We derived it using this algebraic reasoning, but we don't have any algebra here anymore. It's just everything is based in combinatorics. Okay, so just to conclude, What we derived this new set of differential equations for the wave functions in the power law FRW cosmologies. It's purely combinatorial, and the formula which we find is based on the combinatorics of C-tubings, and both the functions and the coefficients in front are related to that combinatorics. And the important thing is that the set of these master functions, or this basis which I used, are twisted integrals of some canonical forms of some positive geometries. And this fact that they are logarithmic forms was very important in our derivation. So that's one of the main differences also with any other derivations which I explained before. We really strongly rely on the fact that everything is based on positive geometries. Now, of course, I just explained to you how to write these equations, but now what we like to do, we would like to also solve them. So that's the next step. That's a difficult problem. There's the way to solve these equations is just, you can assume that each alpha is small and just do this perturbatively in alpha. But, so every stage, at every order in alpha, you get some polylog function. But then you need to resum it, and the resummation can be as complicated as you want. It's a hypergeometric function, usually. Okay? So that's another thing. But the question is, can we use this very nice combinatorics to find some simplifications in the answer as well, not only in the equations but also in the answer. And what we'd like to do is to better understand the underlying geometry, and I can tell you what I mean by this if you ask me. And there's another question which is kind of slightly tangent to that, because here we work on the graph by graph basis. So for every graph we have a set of differential equations. But recently, there are some papers on how to find the how to find the positive geometry which combines many graphs together, which goes under the name of Cosmology. And the question is, can we just uplift this story to Cosmology and just maybe find something there which is even simpler, because it talks about kind of combinations of graphs as well. And then, of course, this was done for the model which is quite toy model. Question is, can we make it more realistic and go away from conformal complete scalar field to more realistic cosmologies? Okay, so thank you.
Questions?
I guess the nicest two examples of graph associahedra are usual associahedra from the path and permutahedra coming from the complete graph. So I wonder if your results look extra nice for the complete graph, or if there could be physical interpretation.
I don't think that there's any simplification in that case for the complete graph. It's everything will be. What one needs to study, one needs to just first study all the set of C-tubings on that. Right? I don't see how for this particular graph there's any simplification. It's just you need to take all possible C-tubes, all possible tubes and the compatibility conditions. So,
but do you think there could be any physics interpretation in this other nice special case?
I don't know really. So for the paths, then there's some. There's some relation to the phi cube, right? But this is like a combination of various pieces of phi cube. It's like gluing together various associahedra to get. So for a given path graph, you need to glue together various associahedra to get a single wave function coefficient. So even here the relation is not so obvious. Yeah, I don't know what. There's nothing to start. Even the amplitudes. So the question would be, what's the relevance of amplitude for a complete graph in physics? And I don't know. I don't know an example where they play a role.
Other questions? I had a quick one. Where is epsilon hiding in this differential equation?
Yes, so the epsilon sits solely in alphas.
Alphas are all proportional to epsilon?
So there's an expression. So depending on every vertex corresponds to some interaction type, right? Yes. And so there is like valency of this vertex and epsilon. And there's a formula which I don't know if I can recall now, which looks something like that. alpha v is something like 4 minus p epsilon, sorry, 4 minus p.
What was epsilon, I think? Because if
Minus 1? No, sorry. 4 minus p.
times 1 plus epsilon, maybe? Because if epsilon is equal to minus 1, it goes to 0, it doesn't depend.
Yeah, I think it's that. It's this one. Yeah, so.
Dobra.
Yeah, I think that's, or maybe there's not minus 1. So such that when p is the valence of this vertex, right? So when p is equal to 3, sorry, there's no minus 1. Yeah, when p is equal to 3, then this is just epsilon.
Okay.
When p is equal to 4, it turns out to be 0. Okay, and then so yeah, so
Okay.
that's the
But
So-
the crucial point of my question, it is in what we call epsilon factorized form?
Yes.
Okay.
Yes. Yeah, exactly. So this is proportional to epsilon.
Yeah.
So yeah. So but the proportionality factor depends on the.
Sure.
And then yeah.
Since you didn't tell us exactly what the R's and T's are, I can't tell just from looking at that formula whether there can be cancellations between terms or not.
No, I mean you can look at this particular example. So for example, the set of regions. So we start with this C tubing, and the set of regions is somehow almost all possible regions of this tubing, plus some regions with with some of the tubes removed. Okay, and I mean each of these functions are, I mean they're not independent, but there are no relations between d logs of them. Okay, so R's are they are dependent. There's some basis for them, but d logs I think are the
And
only.
in your formula itself, can you go back to your formula? Because in principle, literally the same R and tau prime could show up in separate terms, but I guess you're saying that doesn't happen.
In separate terms here. Sorry.
No, in your formula,
Yeah.
like, because you're running over, there's one V, and then you're running over the R's and the taus. So
Yeah. So
you can't get the same R and tau prime for a different.
for different alpha. Yes.
Yeah, okay.
Yes.
That's what I was
That's
asking, because
yeah,
since
yeah.
I don't know what they are, that isn't obvious.
Yeah, but the point is that the regions which you get in front of each alpha know something about the given vertex. So for example, there's only one region here, because there's only one region which encircles vertex 1. And there's more regions here because you can take this region or the one where you removed one of the children. So there's more options here. So that's the reason I split them into pieces. I have 4 more slides in case, just for the open discussion. So I just maybe say very briefly what these 4 slides are.
Let's proceed to the open discussion.
Yes, and we can do that.
We have time before dinner, and if anyone wants to leave, we won't take attendance.
So I just tell you what the 4 are, and then you can leave. Yes. So I mean, we have various questions which go from obvious things we would like to do, and Combinatorics can really help with that. I mean, first, we did it in the physics way. We took a selection of graphs, and then we just ran the algorithm and recognized pattern and just wrote the answer. But the question is, can we prove this formula? It looks like the proof should be quite combinatorial here. So that's question number 1. Question number 2 is, I told you before that when you write the flat space wave function, you can either decompose it into the C tubings or maximal C tubings. There are 2 different formulae where this mu and mu tilde they're quite similar to each other, but they are different, and we couldn't prove that there's an equivalence here. But it turns out that, I mean, just case by case checks, turns out that these 2 formulae are equivalent to each other. So if one understands a bit better what all the C tubings are, maybe this formula will be possible to prove. Now, I told you that there's some better understanding of geometry would be nice. So for example, if you take this graph, so this is a graph with 2 vertices and 2 edges, the canonical form, so this wave function coefficient or the canonical form associated to it, corresponds to some positive geometry, but the positive geometry looks quite strange. It's a collection of two polygons. And if you take some more complicated cases, so for example, if you take path graph with 3 vertices, then the canonical form which you find is the canonical form of 2 polytopes which intersect along a line. And there's no obvious way of finding an explicit description of this geometry. The way we found it is, I told you that the wave function coefficient can be written as a sum over amplitudes, and for every amplitude we know what the geometric interpretation is, and these shapes are just adding and removing various geometries to each other. So for example, if you take this graph and you write it as a sum of amplitudes, there are 4 terms, and the geometries corresponding to that would be something like positive quadrant minus this shape plus this shape minus this shape. So very non-trivial. So these amplitudes, the degenerate graphs assemble in something very, very non-trivial. And the question is, can we understand it a bit better, maybe from combinatorics, but to understand, to have some explicit description of this set.
Wait, but then was it before or after this step? You had this thing where you subtracted. You had the alternating sum, and you added the pieces, subtracted the pieces. How does that play in with this?
Yes,
is that exactly what you just said? Or?
So in this case, there's 7 maximal. 7 maximal CQ beams.
Yes.
And they correspond to 7 vertices of this.
Okay.
So every maximal CQ beam corresponds to a vertex of this geometry. Okay. But because we split everything in some kind of amplitudes for various removed edges, then this is really sum and difference of various geometries.
Yeah, that's right.
Where you kind of add and subtract pieces.
Yeah.
And that's still easy to understand, but if you go to 3 dimensions, it's already very difficult. So some very a bit more explicit way of writing this geometry would be nice. And then the 4th one is the interesting for this community probably the most. Is now the question is there any cluster algebra story here? Because what we wrote some set of letters, and we said that all the letters correspond to these regional variables. And the most general case where when we take the alphas to have any value, it's very difficult to solve these equations. But there are some cases where we know how to do that. And in particular, if you take cosmology in the de Sitter space, which is epsilon equal to 0, and trivalent interactions, that all of the alphas are equal to 0. And for example, for this graph, you can find what the symbol of the solution is, and the symbol is just this. Okay, and then it turns out that so these are the letters, but this is the symbol. If you take cluster algebra A2 and take this as a first and the second cluster variable in your cluster, you can just do cluster mutations, and this is what you get. You get 5 cluster variables. But then if you see that this cluster adjacent, right? In the sense that these two things are sitting in the same cluster, and these 2 things are sitting in the same cluster. So there's a first, second, third, and fourth, and fifth variable. Right? So this is 1 cluster, second cluster, third, and 4th cluster. So it looks like in this case, there's some cluster adjacency. But my question to everybody who ever worked on this or knows the answer is what would be a generalization of this to more complicated graphs, and whether there is some cluster structure on a set of tubings, or these are the very natural combination of variables associated to graphs, and I don't know if anybody knows anything about that. Yes.
An even more basic question is, can you ever get the same answer out of 2 different graphs after change of variables?
2 different graphs.
You start with 2 different graphs.
What do you mean 2 different graphs?
2 different graphs to start with.
Yeah.
G prime, but with the same number of variables.
Yes. So for example, this one. Yeah. So but there are no other. At least in this case, there's no other graph with the same number of variables, right?
Okay. So it'd have to be a bigger example.
Yeah.
Does the graph uniquely specify the geometry, the canonical form, and so on, or could it be that one transforms into another after a clever change of variables?
So I think that
they're actually equivalent to each
I
other.
think that the answer to that would be that there will be different set of letters, because there will be different set of C tubings in that case. There will be no way to transform one to the other, because I think that kind of this cluster algebra should live somehow in a set. It shouldn't be related to this graph, I think. And the A2 and A2 somehow here it's kind of coincidence. But if you take already the path with three vertices, then you get too many letters for this to be A3, for example. So it needs to be something on probably some graph of adjacency of tubes or tubings. I don't know what it is. But in the sense that the answer already for path graph with three vertices is way beyond A3. So I don't know what the story is. But yeah.
Sorry. I mean, you showed an amplitude earlier, and there the poles looked like compatible in the 2B sense. Is that the same adjacency that we're observing in a way?
I don't think so.
Look, I mean the amplitude here. So you see that you can always put the tubes inside each other in each term.
Or they're disjoint, the last time.
Or they're disjoint. There's
Yes.
no intersecting tubes, so that looks like some compatibility. And is that like analogous cluster adjacency?
But the point is that when you talk about this psi FRW, so the twisted integral, so the letters which you get are not really the tube variables, but they are region variables. They are differences of tubes. So here, yeah, I think that this is cluster algebra. It's a cluster adjacency of somehow graph as a hydra.
Okay.
This is graph as a hydra. But the story which is later is much more complicated, because the letters which you get. So in this case, you just get 6 letters, as I wrote here.
C2.
Here. There's 6 letters somehow, right? For the plane wave version. But when you do if you find all the regions, the number of letters is, I don't remember exact number, but it's around 20. So it's much higher than that. So this does not compare to the other one. It's a much easier story, and probably there is an easy answer.
Obviously, it's different. Yes.
Any other questions for Tom? Okay, let's thank him again.